Welcome to the lecture 12. Building upon the molecular orbital concept from our previous lectures, we will now analyze how specific solvents physically induce spectral shifts. The polarity of the solvent plays a major role in electronic transitions. Polar solvents such as water and ethanol strongly stabilize excited states. They achieve this through dipole-dipole interactions. Excited states often possess larger dipole moments than ground states. Because of this, polar solvent molecules align themselves around the excited molecule and lower its energy. This stabilization reduces the HOMO-LUMO energy gap for pi to pi star transitions. As a result, we observe bathochromic shifts, also known as red shifts. Now consider non-polar solvents like hexane. These solvents minimize electrostatic interactions because the molecule experiences very little environmental disturbances. Its vibrational fine structure remains clearly visible. The resulting spectrum closely resembles gas phase behavior. However, polarity is not the only factor. Hydrogen bonding introduces much stronger effects. Protic solvents such as alcohols forms hydrogen bonds with polar chromophores. Carbonyl groups are a common example. Hydrogen bonding specifically interacts with non-bonding lone pairs on oxygen atoms. These lone pairs form the HOMO in N to pi star transitions. Hydrogen bonding stabilizes this ground state strongly. This dramatically increases the energy gap. Therefore, N to pi star transitions show pronounced hypsochromic shifts or blue shifts in hydrogen bonding solvents. Finally, remember one practical rule. Every solvent becomes opaque below a certain UV wavelength. This cutoff wavelength limits the spectral region you can experimentally measure. Let us now formalize the causes of spectral shifts. A bathochromic shift or red shift is the moment of absorption maxima toward longer wavelengths. Structurally, this occurs when conjugation increases, adding exochromes such as aminochromes or hydroxyl groups. Extends electron delocalization. Greater delocalization reduces the energy gap. Environmentally, polar solvents stabilize excited pi star states, again producing red shifts. A classical example is the conversion of phenol into phenolate ion. The added negative charge greatly enhances electron donation, causing a strong bathochromic shift. Now consider the opposite case, a hypsochromic shift or blue shift moves absorption maxima toward shorter wavelengths. Structurally, this occurs when conjugation is lost. For example, protonation of aniline forms anilinium ion. The nitrogen lone pair can no longer participate in conjugation. The energy gap increases, producing a sharp blue shift. Environmentally, polar solvents also induce blue shift in N to pi star transitions through hydrogen bonding. Now we must learn to identify the quantum transitions observed in UV visible spectroscopy. There are three major categories. First is sigma to sigma star transitions, These involves electron in a single covalent bonds. These electrons are tightly bound and require extremely high energy for excitation. Therefore, these transitions occur below 150 nanometers, deep in the vacuum ultraviolet region. They are typically of saturated hydrocarbons like methane or ethane. However, atmospheric oxygen absorbs strongly in this region. Because of this limitation, sigma to sigma star transitions are rarely observed in standard usable instruments. The second category is pi to pi star transitions. These are extremely important for practical spectroscopy. They involve delocalized electrons in double bonds and aromatic systems. They require moderate energy and appear between 180 to 400 nanometers. Examples include alkenes, polyenes, and benzene rings. These transitions show very high molar absorptivity, typically greater than 10,000. The strong intensity arises from high transition probability and electron delocalization. The third category is N to pi star transitions. These involve excitation of non-bonding electrons or lone pairs. Because of these electrons already lie at relatively high energy, only low energy photons are required. These transitions appear between 250 to 700 nanometers. They are characteristic of carbonyl groups and nitro groups. A defining feature is very low molar absorptivity, typically between 10 and 100. The weak intensity occurs because orbital overlap between N and pi star orbitals is poor. These transitions are also extremely sensitive to solvent environment and often show blue shift in polar solvents. Let us summarize the three transition types. Sigma to sigma star transitions require the highest energy. They occur below 150 nanometers and are rarely observed experimentally. They are typical of simple alkanes. Whereas pi to pi transitions occur at moderate energies between 180 to 400 nanometers. They possess extremely high intensity with molar absorptivity greater than 10,000. These dominate spectra of conjugated molecules and aromatic systems. Whereas N to pi star transitions require the lowest energy, they appear at longer wavelengths from 250 up to 700 nanometers. They are weak transitions with very small absorptivity values. These transitions serve as important diagnostic signatures for carbonyl compounds such as acetone. Thank you.